finding the solution. I gave you kind of, guys, as an exercise to go ahead and try to solve the 4 queens problem. If someone ended up doing that, that's great. If you didn't, that's okay. We'll go ahead and be able to compute the lesson here. If you want to try solving the 8 queens problem by hand, that's kind of fun, but admittedly kind of painful sometimes as well. So don't worry about it. You don't have to do it if you don't want to, but if you want to do that while I'm coding this up, the simple print board function, you can do so, because the print board is, in my opinion, not as interesting as what the backtracking is. All right, so the print board function, we're going to have some I variable, we're going to have some j variable. We're going to do a for loop I equals 0, I is less than num, I plus plus, and then we'll go for j equals 0, j is less than the number that we're given, j plus plus, and then what we'll do is we'll just simply print at the contents of that board. So we'll do %d, and then I'll put space between them so that way it's a little bit more readable. Board of I of j, and then what I can do is I can print a new line between these rows. So what I'm doing in this print board function, if you were interested in it because you don't really know how to print 2D stuff very well, I mean, this is something that's good to know, is I'm just looping through the first dimension, which is going to be the I, and then while I'm looping through that, I'm going to move to the second dimension, which is basically going to get me everything inside the I row. And I go through each column basically, and I print this element out, and I put a space in between these elements, and then once I'm done printing out this row, I just do a new line. It looks very nice. If you want to do something more fancy, you can. It's not that hard. I could do something like dividers in between these. I could print out divider at the beginning, or alternatively, actually, this might be a little bit easier to do in code. I can do a divider there, and I can do a divider at the very end. And then I can go ahead and print out actually lines that separate the columns as well. I'm going to go a little bit fancy on this, I apologize, but I just realized that I can make this look really awesome, so I'm going to try to do so. And it's not going to be really awesome, but it's going to be close to it. And then plus sign for the new line character, and then I need to do the same thing at the very beginning. Shift tab that down. All right. So that's going to be the board. Hopefully that will work really well when it's done. Hopefully that doesn't crash and burn on me. So if we're able to successfully find a solution, which we might not be able to find a solution, we'll go ahead and print out that solution. Otherwise, what we can do is we can just tell the user that we failed to print something out. So why not just inform the user that we were unable to find any possibility or possible solution. So print out no solution was found. And hopefully we don't get too much of that message, but we'll see. So for the queens problem, what I had said before is that when you're placing the queens down, you don't ever need to put any more than one per row. So if we're at index, what we should do is we should look at only placing a queen in that row position. So what we're going to do is we're going to go to every row, or to every spot in the row that's at index, which is like the weirdest thing ever, but like, you can imagine like it would be the ith row. And we're going to go ahead and try placing the queen in there, and we're going to check to see if that does something invalid. If it does something invalid, then we're going to go ahead and try a different position. If no position ends up working on this row, then that means that the state that we were given was impossible to solve. And because it was impossible to solve, well, we can't ever solve this. So we'll just return a failure at that point. So I'm going to kind of code up what I was talking about. But we're going to go ahead and try every possibility. So we're going to, for I equals 0, I is less than the num, and we're going to try placing a queen at this position. So what that means is we're going to do board of index, because we're in the indexed row, and then we're going to place something at this location. We're going to say that this is a queen. And then, if this ends up working, so if it is successful to place it at that location, and how we can check to see if it was successful to place it at that location is we just try recursing again, and we go one more index down. We place the queen down. We still have the same number of queens we need to place, and the board's going to remain more or less the same. Then what we do is we have a successful board, so we will return a success as well. If we were successfully able to place the queen there, then Awesome. Continue. If we were not successful, so this is a fail state, and we know that we'll be here in a fail. So here in a fail scenario, what we'll do is we'll just go ahead and empty that spot on the board. So we'll say board index of I is equal to empty. And this is kind of this is the backtracking step. The idea is that we weren't able to solve it by placing the queen at that location. We go ahead and empty that spot, and we move on to the next location. So we empty it, we backtrack, and we repeat. If we're down here at the end, and no position was successful, then what we need to do is we need to very simply return a failure. So I'm going to go ahead and pound define a few things now. Pound define success will be a 1. Pound define failure will be a 0. Pound define queen will be a 1. Pound define empty will be a 0. And so now I have several different things defined here. Hopefully it'll make this make a little more sense to you guys what's going on. I'm going to have to make that variable I. And what I really need to do though is every time I enter this recursion, I want to make sure that my board has been valid. Because if my board is not valid, then that means that something bad's going on. I'm placing the queens illegally. So what I want to do before I enter this loop is actually check that I have a valid board. So if it's not valid board num, then this is a problem. So what I'm going to do is I'm going to go ahead and return a failure as well. And this will mean that if I place a queen down immediately at the wrong location, then I don't have to do any more work. I know that this is bad. I don't have to like really worry about anything else. I can just go ahead and say, hey, this is a bad board that you gave me. There's no possible solution. So check for an invalid board setup. And then what we can do additionally is if the number is equal to the index, in other words, if we place all of the queens down, what should we do if all the queens have been placed and this is a valid board? Yeah, this is a successful position. And so these are the two situations that we really need to worry about. But you might notice that there's something now missing. Try all possible placements for the queen. So what's missing now from my code? Yeah, I don't have any way of doing this right now. So I need to make a new function, unfortunately. So I'm going to go ahead and very simply pound define true. So for those of you that don't know, if a valid is ever, a non-zero value is ever passed into an if statement, the value is true. So I'm just going to go ahead and use true to denote that it's true. And if it's 0, that means that it would be non-valid. So false is going to be 0. So what I need to do is I need to make the, oh sorry, I forgot to actually put the prototype up here. So int a valid function. The valid function takes in the board size. I can spell. And then takes in the number of positions, the dimensions of the board. So that way we can go through the board and make sure that everything's good. So I'm going to go down to the bottom and then begin working on that valid function. So int valid, it takes in the board, takes in the dimensions of the board, and then we'll hopefully return something. So what I want to do is I want to check to make sure that no queen is attacking another queen. So what we can do is we can just loop through all positions of the board. I'm going to do this very inefficiently, just so that way we can get the idea across, not worry about the efficiency right now. There's like much better ways of doing this, and I can discuss that later if you want to know about it, if you want to learn about it. So what we're going to do is for I is equal to 0, I is less than the dimensions, I plus plus. For j is equal to 0, j is less than the dimensions, j plus plus. And then all I want to do is I want to check to see if there's a queen here. If there is a queen at this position, then that means that I need to make sure that this queen can't attack any other queens. So if board of I of j is equal to a queen, then I need to go ahead and check to make sure that there's no queen that can be attacked by this one. So I can attack everyone that's in my row. So what I'm going to do is I'm going to go for, I need to make another variable, darn, int ii. For II is equal to 0, II is less than the dimensions of our board, II plus plus. And so what I want to do is I want to say board of II. Now this should never be the case, but if board of II J is, well actually this one might be the case. Board of I is equal to queen, sorry. So if there's someone that's in our same column, because we're keeping J constant, then that means this is a queen that we can attack. So we're going to go ahead and return false. But this doesn't always work. Does anyone know when this is going to fail? Yeah, it will. So if I and II are equal to each other, then we're going to have two queens that are in the same column, but they're not in the same column because it's the same queen. So what we want to do is we want to make sure that I and II are not equal. So in order to say that they're not equal, what should we do? Not equal, right? All right, easy. Oh boy. Does this make sense? Is there anyone that's lost or confused what I'm doing in this step right here, right now? No? Yeah, what's up? The brackets? Yeah, there's a lot of them, right? So, this here is going through all rows. This is going through all columns. This here is checking that there's a queen. This here is now checking the column of the queen. If there's another queen in this column, that means that's invalid. So this here would be find another queen. And it has to be a different one. And that's why we did the not equals thing. So we're not even done yet though. Because this is just the column check. We also need to do the row check. Because the queens can attack things that are in their row as well. So this is pretty easy. What we're going to do is we're going to make a variable jj. So jj is going to be equal to 0. jj is going to be less than the dimension. And jj is going to be plus plus. And then if it's going to be jj in this case now. If j and j are equal to each other, then we won't want to check this. And we don't do II anymore. We're keeping I constant. We're going to be in the same row. But we're going to check to see if there's another queen in this row. And there shouldn't ever be another queen in this row because we're only placing one queen down per row. But as a sanity thing, I'm going to go ahead and do this just to make sure that we're not going to have another queen. If this ends up happening, something horrible has gone wrong with the code. And that's going to be a problem. So maybe I'll go ahead and print oops. And if we get a lot of oops, then something's gone wrong. Hopefully, we won't get a lot of oops. All right. So then the last thing we need to check is what? Yeah, diagonals. They're so much fun to work with. All right. So the thing about diagonals is that we need to go ahead and whatever value we're at, we need to go in the, if we go in the forward diagonal, that means that we need to go ahead and add to both the row and the column. If we go in the backwards diagonal, that means we need to add one and subtract from the other. So another thing we need to make sure that we can do, though, is that we don't just want to add jj to both of these. Because the thing is, we might be further back on the diagonal as well. I guess technically, if we're doing this correctly, we don't need to do that because we're always going to be going in one dimension. Oh, that's disgusting. I don't like that. I'm gonna go ahead and check both directions anyways. So how we can check both directions pretty easily, and this is going to be really disgusting, is we can actually do two for loops. So what I can do is I can do for II is equal to 0. We can do this. There we go. And this is really inefficient, and you probably shouldn't do this. So this was checking the row. And this is going to be checking the diagonals. But this is very, very inefficient. So what we can do is if this is on the same diagonal and if these are not equal, so if jj is not equal to j and II is not equal to I, and we need to somehow check that they're on the same diagonal. So if we're doing a forward diagonal check, it's pretty easy. We need to make sure that basically the difference between these two guys, the difference between our rows and our columns are equal to each other. So what we can do is we can just go ahead and subtract these two from each other and check to see if the subtraction between these two are equal. So I know that sounds a little bit weird, but this is going to be the forward diagonal. And the idea is anywhere on the forward diagonal, you're going to be offset by the same amount in both directions. And so we just need to check basically the dx and the dy. And if the dx and the dy are equal to each other, you can think of it kind of like as a slope thing. That means we're going to be along the same diagonal. So we're going to check the dx and we're going to check the dy. And if they're equal, then we're on the same diagonal. And then we need to check to see if there's a queen there. So I minus I is the dx. If this is equal to j minus j, then that means that it's equal to the dy. And then we need to check to see if there's a queen there. And I'm going to put this on new line. Boards of II of jj is equal to a queen. Then this is a problem. And so what we need to do is we need to go ahead and say that this is an invalid state. So we're going to go ahead and, return false. So this is for checking the forward diagonal. Now we need to check the backwards diagonal. Is there any modification you guys can think of that can do to very easily check for this backward diagonal? Let me go ahead and change this word. Kind of, sort of. So it turns out that when you're going on the forward diagonal, you're at like a positive slope, which means the dx needs to be equal to the dy. If you're on the backwards diagonal, that means that you're going in this direction. And what type of direction is this? Like, what type of slope is that? It's a negative. And if it's a negative slope, then what does that mean the dx and the dy need to be like with respect to each other? Yeah, they're going to be the additive inverse, which means that they're going to be the negations of each other. So if we actually want to go ahead and check to see if these are equal to each other, if they're on the backward diagonal, we just go ahead and check to see if one is the negation of each other. And all we do to do that is we just do j minus jj. And so this is going to be checking for the backward diagonal. And if there is a queen at that location, then we'll return false. And then at the very end, outside of all of these crazy loops, if we never found a conflict, then that means that this is a valid board. So we'll return a true. No, the reason why is because if we did I minus II, then that means that we're checking to see if the negative dx is equal to the negative dy. But we want to check to see if the negative dx is equal to the positive dy, because we need to go ahead and make sure that they're like the negation of the slope. If you ended up checking if the negative was equal to the negative, then that's like the same thing as doing the one above, right? Yeah. All right. So this should be all we need to do, hopefully. Oh, there is something I'm missing. It's very important. I don't have a board. So let's go ahead and do that real quick. Int star star. Oh, actually, I'm going to cheat. All right. I'm lazy today. So I'm going to go ahead. Oh, no. I'm sorry. There you go. So we're going to go ahead and do int board of num queens. Of num queens. I don't have to do any dynamic allocation. Yes. Little successes. You're right. All right, and then there is one other thing you need to do. What is it? Yeah, what's up? Yeah, if I did the absolute values, then I would only need to do one check, right? Yeah, but we're not doing that. All right, so that's one way that this is slightly inefficient. Another way that it's slightly inefficient is you can actually get everything to be in constant time for doing the checks, which is pretty awesome, but it requires a little extra memory, and I'm not doing that, so it's a little unfortunate. So. Yeah, I'm doing like n cubed for the checks. Actually, I'm doing n to the fourth for the checks, so it's really slow. But there's ways to get it faster. All right, let me delete that and delete that line. So I need to make this board empty initially. So what I need to do is for I equals 0, I is less than num queens, I plus plus. For j equals 0, j is less than num queens, j plus plus. And then I'm going to say board of I of j is equal to the empty spot. And then you can make an I and j. There's so many things to do. All right, I, j, there we go. All right, and let's have this not work. GCC queens, is that what I called it? Yeah. Ugh. Oh, ha. Lol. All right, so I don't want this. I don't want this. And then expected int star star. Oh, but I did the weird thing instead. Aww. Alright, dynamic memory, just makes me so sad doing dynamic memory sometimes though, because I never clean it up. I'm a messy dude. Alright. As in, I eat soccer players. I'm kidding. Alright, this needs to be num queens and size. Size of int. Alright, and then I need to do the same thing here. It's equal to int star star italic num queens comma size of int star. Alright. And so, what are you going to complain about this time? Oh wow, it's really close. Oh! Where is it? Okay. And then boards. Did I misspell boards or something? Oh, it's not supposed to be plural. Where did I put that at? There. Put it in 2 spots. I did not copy and paste these lines. You can't read anything. All right. Yikes. All right. Cool. Yeah. So we need to say how many queens we're doing. So let's do something simple. We'll do 4. Okay. Is that correct? It's really hard to see because of the zeros and ones, right? I'm going to cheat a little bit. Where is it? So there we go. I'm going to go ahead and make this S. And then what I'm going to do is... Sorry guys, it's just me being pedantic. So if it's equal to queen, there we go. Alright, you guys know about ternary operators, right? No? Well, here's a perfect time to learn them. So ternary operators is a really cool thing where you give it some Boolean function, and then you put a question mark, and then you give what you want it to return on a true value, and you give it what you want to return on a false value. So if this is a queen, then I'm going to return a q as a string, like a constant string as well, so a constant char star. And if it's not a queen, then that means I'm going to go ahead and return space or an empty spot. So you always do a Boolean value, and then what you want for trues, and then what you want for falses. So you need to make sure that if you're doing this, that you're doing it with the same type. Like it would be weird if you had a string return on a true value and then a number returning a false value, as long as you're expecting the number to be cast as a string, I guess. But yeah, just be careful with that in general. But this is how you can get away without doing if statements inside print things. People normally don't like doing that, so it's okay if you don't like it. So A got out, so we're going to go ahead and do 4. All right. Looks a little better, right? So is there any queens that can attack each other? It doesn't look like it. All right, cool. So let's try one more thing. Is there any suggestions you guys have for me?
69.
I heard 42. I don't like that. I heard 21 as well. Taking a little bit too long. Oh, wow.
I don't think that works.
Did it? This looks really crazy and random.
Can we do a review?
I said that it would take a long time. It would crash normally if you were doing something that was straight for permutations, but because this is optimized, it's doing the backtracking, it's actually able to run fast enough. If you did something like 26, you'll probably never see it finish. It won't crash, it'll just hang forever. I think I did one time an entire lecture when I had it run on 28, and I just kept going, and at the end I killed it, because I'm like, it's taking too long. But, so that's going to take a long time. We're not going to worry about it. This is basic backtracking. Let's not go ahead and do that. Instead, let's go ahead and run 8, because that's like the common problem that people like to ask. Like, how do you do 8 queens? And it turns out you can place a queen in the very first spot. And it doesn't look like there's any queens attacking each other. No, I'm not like an expert in chess, so, I mean, I could be wrong. But this looks like it's working, so cool. I can go ahead and double check that it's working, sort of. Let's see what happens when you do 3. 2? What? 1? Hey! Alright. So that's enough of that. I'm going to go ahead and switch over to some things regarding the exam. So this is backtracking in a nutshell. It normally uses a valid function, and it also normally uses some form of recursion that is very similar to permutations. And what it does is, I'll just bring it back up here. You go ahead and check to see if it's valid. If it's valid, or if it's not valid, you return that as a failure. If it is valid and you're at the end, then you can return a success. Otherwise, you just try all possibilities, and every time you try a possibility, you check to see if that possibility was successful. And if it wasn't, you go ahead and erase, you backtrack, and then what you do is you return a fail if there's no solution possible. And it might be because like the position of the queens you were given were in a way such that you can never find a solution. So this is very useful to put in. Not many people know to put that in, and they end up doing backtracking wrong. So try not to forget that. So a few things that I want to go over before I do this, and like you can see where I got this from. But anyways, I want to go ahead and just say that we are having an exam sometime soon in this class. Does anyone know when it is?
Wednesday.
Yeah. Let me switch over to overhead. All right. So it's not Tuesday. It's Wednesday. My dudes. Wednesday. Yeah, so if you're curious, what I recommend do is Google search UCF final exam schedule and then input our stuff into there. Maybe that's something I can just like do really quickly for you guys. Just so that way we're 100% certain. Because I hate telling people the final exam time because I'm really afraid that I'm going to like say the wrong time to the wrong person. I think it is as well, but let's just go ahead and double check. So what I did to find this is I typed in like fall 2018 UCF exam. I think you can literally type in final exam schedule. And like it's still like the first thing, surprisingly enough. No, don't tell me anything. Alright, so when you go here, you can then go ahead and say what our pattern is. What are we class-wise?
Monday, Wednesday.
NW, what time?
6.
7:15.
6, and then it's the 7:15, right? It's a 75-minute class. So this is the time. So it starts at 4, and it ends at 6:50. It's in here. In here.
In here.
Yes, it's in here. It's not my office. Don't go to my office.
Can we try?
We all go to the...
All right. What do you need to bring? So you need to bring in a pen or a pencil, your UCF ID, and a formula sheet.
Calculate.
2 of them. So you get 2 sheets, front and back, so 4 sides effectively. 8 by 11, 8.5 by 11. Don't bring in something huge. Don't bring in a target receipt that has like stuff written on it for your formula sheet. I mean, it's funny, but it was only funny the first time. It won't be funny the second. Please don't bring in like some random long piece of paper. Not cool. Another thing that was really funny, and it's the reason why I say, you know, front and back now for the sides is like someone one time did a sheet that they did the Mobius strip thing on. It's actually kind of where the thing came, like motivation came from the assignment. And they're like, it's one side because it's all one side. And it's like, no. Throw that away, get a new one. It's going to be 8 to 16 questions. And it depends really on how hard I make the problems, whether I do more or less of them. No calculator, no computer. So yeah, that's a lot of things. I'll go ahead and write some of them here. Pen, ID, 2-page formula sheet.
I know, right? Here, let me just do
4 sides, effectively. Because you can do front and back.
This is going to be 8 to 16 questions.
And additionally, typed or written.
That's a huge ass fucking jump.
And this means you can put pictures on there as well, if you want to. I don't care as long as there's no links. And yes, no calculator.
Boo.
No computer. Yeah, forget you two. Alright. So it's going to be a 2-hour and 15-minute exam, so be prepared for that. Please use the bathroom before coming in here. If you're going to do something really crazy, don't like decide to do a cleansing before the exam, not cool. I don't want to have one of my TAs sit outside the bathroom for 50 minutes. Alright. What time?
I need to take a shower.
4 p.m. Is it cumulative? Yes, it is. It's going to hopefully be 25, yeah, forget you. All right, 25% exam 1, 25% whatever was on exam 2, and then it's going to be 50% of the new material.
Oh, yeah. That's a lot.
So this is the rough breakdown of what I'm hoping for, what I'm shooting for. It might be a little plus or minus, maybe up to 28% on one of them, but whatever. It shouldn't be that bad. And like some of these concepts can very easily overlap with others. Like I can ask you what the runtime of a heap operation is. And runtime is stuff that you did in the first section, and it's technically stuff we've done in the newest section. So you can expect a little bit of intermingling. They don't have to be their own separate camps. All right, let's go ahead and work on this like practice exam, and then I'll hopefully be able to knock out another exam for you guys. So I'm gonna like do 200 points worth of solving in 50 minutes. Less than that, 45. All right. So what is the big O runtime in terms of n for the following segment of code? So the first thing we need to check is what's going on here. This looks pretty obvious. This is going to be like some linear operation that we're doing, assuming that this is constant time. You should assume that an array access is constant time. That's like something that we like to use a lot. So what's this here?
Probably like in.
This is O of n as well.
You're gonna fail it.
Is it? This is O of n squared.
Whoa. Okay.
Whoa.
Why would it be O of n squared?
I guess you're gonna pass.
Yeah, so it goes back to the beginning. But the thing is, it goes some distance until it gets to reset, right? So it starts at 0, it goes up to 0 and resets. It goes to -1. So it goes back to 0, it goes at 1, and then it resets. It goes to -1. It goes to 0, then 1, then 2, then it resets. 0, 1, 2, 3, resets. 0, 1, 2, 3, 4, resets. And so the idea is that you're going to be doing one operation for the first guy. You're going to be doing 2 operations in order to get to the next one. You're going to do 3 operations for the next one, 4, 5. Does this pattern look similar to you guys? It's going to eventually take n operations to go ahead and set the last element of used to be equal to 1. And the thing is, once it sets it to 1, it never will set it to 1 again. It will always be set at 1. But the thing is, we need to walk past every person every time we do this loop. This is for, in order to set used of 0 to 1. This is to go ahead and do used of 1 to 1. This is to do used of 2 to 1. So this total thing, though, if you think about it, this is going to be n times what? And so the thing is, this is like n squared over 2 plus n over 2. But this is still in the big O of n squared. And so this runtime is going to be big O of n squared. Yeah, already off to a bad start. Cool. All right. So explain at a high level how a heap-like data structure can be used to sort an array quickly. The reason why this is on the practice test, besides the fact that it was on the practice test in the summer, and I didn't want to move it around, but the reason why it's on this one, not the real one, is because I've actually already gone over this problem in class, but I did it on the Thanksgiving day. But as it turns out, and so the heap sort is something that we can end up using here. And the idea is we just fill a heap. And the idea is, like, normally we're using a max heap in this class, so fill a max heap with all the values we want to sort. The last value in the array is always the maximum element in a sorted array. And additionally, the first element in a heap, a max heap, is always the maximum element, which means the first element in our heap is going to be the last element of our array. So take the top element and stick it at the end of the array, and then remove said element from the heap. Now when we remove the element from the heap, what's going to be the new top element of the heap? A lower number, but it's going to be the largest element of whatever's remaining. And because it's going to be the largest element of whatever's remaining, that's going to be the second to last element of our array. So that means that this top element is now the new last element. So what we can just do is we can actually repeat this process, where we take the top element of our heap, we stick it at the end of our array, and then we go ahead and repeat. Very simple. It's like the shampoo bottle instructions, right? You just stand in there forever, lather in your hair until the bottle's empty. No one ever does that? Okay. So all we need to do is we just repeat at this point. Yep. This is because we're using a max heap. If we're using a min heap, we'd be storing it from the front to the beginning. And in fact, it's probably easier for you guys to implement a min heap on the most recent homework assignment than a max heap. It's not that hard to change a max heap into a min heap. All you need to do is go into the reheapify function and change all the greater than signs into less thans, and all the signs that were originally less thans into greater thans, which can be done with like a control F find replace type thing. So this is like 1, this is step 2, this is step 3. So you just go ahead and do this until heap is empty. And that's it. Very easy. So what's the runtime for this?
Log n.
Yeah, so as it turns out, taking an element out of the heap, because we're going to be removing it, that's going to take order n, log n time. And we're going to be doing this n times because there's n different elements inside our heap, array. So the idea is that this step here is going to take big O n log n for all elements. This here, for all elements, is going to take big O of n, because accessing the top element of an array should be order 1. And we're going to be accessing the top element, or the top element of the heap is going to be order 1. And we're going to be accessing it n different times, so it's going to be O n total. And then if we want to fill a heap with all the values, it's going to take log n time to insert each one individually. And so it's going to be n times log of n. So it's going to be big O of n log n. And this is going to be in the worst and the average and the best case. And so in the worst, average, and best case, it's always going to be the sum of these 3 elements. And the thing is, the sum of all these elements, the dominant term, is going to be the n log n's. So it's going to be big O of n log n in worst, what was that? Worst, average, and best case. Wow. All right, so that's it for that. Pretty easy, I think. Now is everyone's favorite part.
Yes.
Postform. This is pretty simple, I think, right? I feel like this was on the first exam.
It wasn't. So you can put it on this one.
All right, cool. Just figure double check. All right, so what we do is we take this d, we move it over here, and then what we do is we solve this. So it's going to be the sum of I equals a to d of d times the sum of j equals 1 to c of 1. This is a very easy one to solve. This is going to be just the sum of I equals a to b of d times c. C, not whatever that abomination was. And so then with this, we can go ahead and move the c and d out. So we have dc out here times the sum of I equals a to b of 1. And the thing is, we don't really have a general form. I mean, we do have a general form for where we have these different bounds on our I, but like it's very easy to just do the conversion. So what you can do is you can say this is equal to dc times the sum of I equals 1 to b of 1 minus the sum of I equals 1 to a minus 1 of 1. And this is going to be equal to dc times b minus a minus 1, which is going to be dc of b minus a plus 1. Not that bad. The best and worst case runtimes for the following algorithms. This is going to be tricky, actually. So what's merge sort? I'll go ahead and separate it where it's like best is first and worst is, or yeah, best is this one and then worst is going to be over here. All right. So what's the best case for merge sort? Log n. Yeah, log n. Yeah. Yeah. Because like the idea is this is for every element we're going to be doing this. All right. What about selection sort?
Professor Travis, one moment, please. I swear to God. Can you just zoom in just a little?
Oh,
Yes, thank you.
I didn't realize it was that hard to see.
No, it's just me.
Okay. Sorry. Is it better?
Yes.
Okay. So what's the worst case runtime for merge sort? Yeah, it's n log n as well. All right. What's the best case for selection sort? I think that's the one I was actually working on, or whatever. So, what? So selection sort does what? it looks for the smallest element, and then what it does
What's with your phone?
is it selects the smallest element and moves it into the very first spot. So the thing is, in order to go ahead and find the smallest element, you have to run through every element in the array in the first pass. And then you need to run through every element in the array minus 1 in the second pass. And the third pass, you need to do n minus 3. And so actually, in the best case scenario, this is not a very efficient algorithm, is going to do n squared. And actually, for the worst case, it's going to be O of n squared as well. And the reason why is because selection sort doesn't do anything different depending on the array, because it always looks through every element to find the minimum element to go ahead and move it into the first spot. What about quicksort? What is quicksort's best case runtime? This is n log n. And the reason why this is n log n is because it needs to find a pivot every time. And the thing is, if you're doing optimum pivot selection, it's still going to take a logarithmic number of steps. And then every element is still going to be compared on every single one of those levels. And so you're going to have log n number of levels, and then every element is going to be used on every level. So it's going to be n times the log n to go ahead and do all the comparisons. What about the worst case runtime for quicksort? It's going to be n squared, and it's n squared if you have bad pivot selection. If your pivot is always the maximum or the minimum element, then you're always going to have to go one element less and then repeat the process. And every one of these levels is going to take n operations on average. And because of that, it's going to be n levels of n different operations, which is going to be n squared. All right, so bubble sort, what's the worst case, the best case runtime? So the one I talked about in class is n squared. The ones that a lot of people have probably seen before that go ahead and break out and there's no new percolation, that would technically be order n. But for our class, because of how I described it and how I didn't say that it was optimized, it was going to be n squared. And the reason why I don't like to say, oh, bubble sort's like best case order n, is because the optimization that bubble sort really does is just it checks to see if the array is sorted, and if it is, it breaks out. And you can add any one of those optimizations to any other sort, and it would still be order n on those sort set in the best case scenario. So it makes me a little uncomfortable when people say, oh, bubble sort's really best case n. It's like, it doesn't feel like it. What about the worst case for bubble sort? And then insertion sort? What's the best case? So why would it be n? So insertion sort, what it does is it has an array, and it looks at the last element of the array. It looks for its position inside this tiny subarray that's already sorted for this element. If this element is already in its position, if it's already sorted, it doesn't actually need to move it anywhere. And it actually just does one operation to check to see if it moves it, and realizes it doesn't need to do that. And it moves on to the next element. And so the idea is that if it takes only one operation for each one of these elements because the array is already sorted, then it'll take only a total of n operations to go ahead and insert the entire array. And so everything will end up being sorted, which it doesn't actually need to do any operations for. But yes, the idea is that this is going to be order n operations, because if you give it something that's already sorted, it doesn't need to do any insertion because everything is already in place. What about in the worst case? And why is it n squared? Yeah, if it needs to move every element, if it needs to move to the front, imagine you have a reverse sorted array. If every element needs to move to the front, then that means it's going to take one operation on the first one, then 2 for the next one, 3, then 4, then 5, then 6, which is something that we've seen as a common theme quite a bit on this exam already. And so the idea is that it's going to take n squared plus n divided by 2 operations, which is going to be big O of n squared. All right. So now we're going to create a binary search tree by inserting the values in the given order. So we're going to insert 5, 43, 79, 35, 33, 47, 16, 68, 96, and 61. That's going to be a lot, right? And then it wants me to draw each tree after insertion. Yikes. Well, the good news is, what is this not? It's not balanced. It's not ADL. So that's a little bit of a relief. But that's still a lot of elements. That was a dick. All right. 55, 43. Where's 43 inserted? To the left of 55. And then when we insert 79, where's that going to be at? The reason why I'm writing like this is because I know how much room this problem ends up taking. All right. Where does 35 end up going?
The left of 43.
So 43, it's going to be to the left of it. So 35 goes down here. This is going to be 55. This is going to be 79. Then 55 is going to be up here. Where does the next element go? Yeah, this is a very interesting graph.
It's gonna keep on going.
Not really. Looks kind of dumb. All right, I'm one to judge. Where does 47 end up going? Oh my god, it's going to be interesting now. So now we have 55 here. We have 43 here. We have 45 here. We have 79 here. We have 35 here. And we have 33 here. You know what? I'm going to emphasize which ones have been inserted to make it a little bit easier on you guys. 47. That's what I said. All right. This one was inserted here, this one was inserted here, and now this one was inserted. All right, so it's a little bit obvious what's going on, but not really, because that's like horrible looking. All right, where does 16 end up going?
All the way.
Oh my gosh, this is the worst tree ever. Things in the way. There we go. This is gonna be bad looking. All right, close enough. And I wrote it right that time. And that one's the one that was inserted. So now we insert which element? 68. Where does 68 go? So it needs to go to the right here, and it needs to go to the left on the 79. So 68 goes here. 47, 35, 33, and 16. So that's the element that was inserted. Where's the next element go? 96?
Probably won't. A bunch of these. Of the 16
Alright, and then where does the last element go? So it goes here, it goes this way, and then it goes to the left of 68, not to the right. You're trying to make my tree look terrible. I'm doing a good enough job already. 96, 68, 61, 43, 47, 55, 31, 16. That's what I said. That's not what I said. Alright. Yeah, close enough. That was horrible. I remember doing that the first time and I ended up having to get a second sheet of paper out because I didn't realize how big it was going to be.
Oh yeah.
It's so easy though. I hate to make it with 25 points and then have someone do something like I did where I messed up the number on one of them and everything is wrong afterwards. Like, would you want that to happen? What's up?
Sure.
Yeah.
Would you be able to do something kind of like the, I think it was, whatever the second exam, like create a tree off the...
Oh yeah, I actually have the second exam with me. I'm going to fill it out in a couple minutes. Hopefully soon. Alright, so yes, I will do that. I'll get to it. Alright, so here's like your favorite question ever, right? Alright, so what I did for this problem when I was solving it, and I think it's like the easy way of doing it, is, well, first of all, we're going to be doing a postfix expression, and we need to draw the operation stack. I gave a huge hint on this question. We need to put operations in these stacks, not numbers. And so because of that, we should be able to figure out what we're doing here. Normally, if you're only doing an operation stack, what you're going to do is you're going to be outputting the numbers almost immediately. It's a pretty easy thing to work with. So what we're going to do, since we need to create a postfix expression, we're going to go ahead and do something very easy. I'm going to go ahead and walk through this, and hopefully we'll end up getting everything done. So at the 5, what do we end up doing? Output immediately. Alright, at the star, what do we end up doing? We put it in the stack. I draw it next to the stack, so that way I don't like screw things up. Technically, if this is a stack, I didn't say which one was the top or the bottom, so I could also like say this star goes down here. I don't know. I guess like whatever you want. As long as it's obvious what's the top and bottom of your stack, it'll be cool. I might even label it on the exam so that we have to go out in a very certain way. But some people draw the stacks going from the top, and they're weird, and I'm not weird, so I'm going to do this. Alright, so now we get this parentheses, what do? We don't pop anything? Okay, we get to the 8, what do? Alright, what do we do when we get to the minus sign?
Put in the stack.
I feel like you guys are just telling me to push everything. What do we do with this one? Alright. 9.
Don't be so.
Output.
The slightly shorter minus sign.
Stack.
Alright, what do we do with this 2?
Output.
Alright, are we gonna do anything ever? Like, I mean, I feel like I've been doing the same thing over and over again. This can't be right.
We're gonna pop it. Sure. We're gonna
Pop it. You gotta pop.
So I pop, and what do I do when I pop
Drop
them?
and pop.
So I do the minus sign, and then I pop the parentheses and draw it here as well? Okay. So these are gone now. Alright, so now I'll draw what my stack is, because it says to, after each one of the closed parentheses. So after the closed parentheses, this is what we have. Alright, and so now what do we do? So we have like a star, then a parentheses, a minus sign. We push the star onto the stack, and then we get the 3, what do we do?
Monday.
By the way, why didn't we pop the minus sign? Yes. So the thing is, because the minus sign has a lower precedence than the star, we push the star on top. Because the idea is that things that go on top always want to have a higher precedence. And the reason why you want them to have a higher precedence is because the things that are on the top of the stack will occur first. It's a last in, first out, or a first in, last out type of data structure. So the idea is the ones that are on the top of the stack will end up being the ones that get executed first. And so then you want the higher ones, the precedence ones to be executed first. So you want to push the higher precedence ones on the top of the stack. A little bit weird, but don't mind it. All right, so now we get to this parentheses. What do we do? Yeah, we pop everything down to the parentheses. So we use star, minus sign, and then the parentheses will get eaten as well. And so I have just a star left. It's very sad looking, but whatever. It's so lonely. All right, so now what do I do? I'm at B. I get to another star. What do I do? So I need to kill this star and then do another star. And when I get rid of that star, I need to output it. So now I get to the parentheses. What do I do? Push, and now what do I do? 4. What do I do with the plus sign? What do I do with the 6? And then the parentheses? Output the plus, remove the parentheses, and then that was at the C, so now we need to output whatever was in our stack. It looks like the same thing. Looks like someone's like doing minimal effort. I feel like you had so many things in our stack at one point, and it's like everything in here is like empty. Whatever. Alright, so now what do we do with the minus sign? Yeah, we push it on top of the star, right? The reason why is because the star has a higher precedence, and the thing is, it needs to occur first, and so we need to pop the star off before we push this minus sign. So this is a bad thing to do. So we need to go ahead and do the star, then we push the minus sign on. Alright, so now we get to the 1, what do we do? And then we're done, right?
No.
Oh.
Pop everything.
Alright. Sorry. Okay, now we're done, right? Alright, cool. That was a nail biter. You guys want to do all of these on the exam, right? Like 10 of these questions?
Yes. No.
Yes?
No. What?
Alright. So this is the hardest question on the exam.
Binary search trees.
You guys ready for it?
Binary
No,
search
10 of those
Okay,
I
good.
could do.
Me neither.
Don't test that. I could do that. That's the easiest one.
Alright, so what I recommend doing for this equation, or for this problem, is to go ahead and draw what happens on a very simple linked list, and try to figure out what's going on. Alright? So, assuming that this is the front first, imagine we called fun1 on 1. So, is this front value equal to null? Is the next value equal to null? So, then we go ahead and we store some next value. What is the next value equal to? It's the next element, so it's basically 2. It's like the box that contains 2. What does ret end up doing? Ret is equal to fun1 of next. So what's going on here? Yeah, we're recursively calling a function with fun1, and what are we calling it on?
Next.
Which is 2, yeah. So we're going to do fun1 of 2. Alright, cool. So is the front value equal to null?
No.
Is the next value equal to null?
Nah, bruh.
Ooh, okay. What's the next value equal to?
3.
This is not the same next value as this guy. That's something very important to note. These are two different nexts. Yeah, isn't that crazy? That's something that not a lot of people realize, I guess. Alright, anyways, so then what do we do after we set the next value?
Look at the next one.
We recursively call again.
Nice.
And so what we need to do is we need to go ahead and do fun1 of what?
3.
Of 3. Yes, I'm so enthusiastic today, guys. Alright, so now, is the front equal to null?
No.
Is the next value equal to null?
Yeah, bruh.
Alright, so what do we do?
Return the front.
Return the front.
So we return front from this guy. So this guy is now returning the value 3, right? So what do we do with this element now that we got this element? Red is equal to this element. So red is now equal to the box 3. And we kind of can ignore this at this point. We don't need to worry about that anymore. So now we say next value is equal to front. What? Are we? So what's the front element inside fun2 or fun1? That. Yeah, the next element is 3's next value, and the front element is currently 2. Because you can think that front is equal to the box that contains 2 at this point, and in here, front is equal to the box that contains 1. So what we're doing is we're saying the next value of 3 is now equal to 2. So that means that 3, in this spot here, we're saying 3 points to the value 2 now. Which is still a little weird, I think, right? And then what do we do?
You have to keep on going.
So what was front here?
2.
So 2 now points to null. Where does 1 point to? 1 points to 2 still. So you can imagine that at this point here, this is what's going on in our guy. It's a little weird, right? So what do we end up doing at this point? So we return red, which is 3. So that means that 3 is coming out of here. And where does 3 end up going into? Yeah, it goes into red again, right? Which is weird. So it's almost like we're doing a substitution of sorts. So red is equal to the box 3, and you can kind of ignore everything that's been going on in here. We don't have this data anymore. It's lost into oblivion because that function is returning, which is going to be great for the people that are doing this online. Okay. All right. Yeah, the jokes are awful. All right. So now what do we do at this point? We're here, and we're inside fun1. We've just set the red up, and now we need to do the next is equal to front. So what was the next value in this position? 2. So next value is equal to front. What was front? So now 2 doesn't point to null anymore. 2 points to what? So 3 points to 2, and 2 points to the element 1. And 1 still points to 2, weirdly enough. It's like some really weird arms crossing thing. I don't know. So now we have front next is equal to null. What's front? So 1's next value is now... So now we have the data structure look like the following.
What the? Didn't we just have that before?
And now we return what? Which is 3.
Wow.
Can you like draw some?
It's now the head. So what we just did was we took a linked list that was 1, then 2, then 3, and we turned it into 3, then 2, then 1, and then we returned 3, which is now the head of this linked list. So we know what it looks like this function is doing to me.
Counting backwards?
It's reversing the linked list.
I'm just gonna take a picture.
All right. So, yeah, that's all it does. Trivial. Oh no, I quit.
You quit? No, bro, we gotta do
No,
the
not
exam
that
2. We
bad.
gotta do exam 2.
Not there. We gotta do that.
Wait, this isn't bad though.
No, it
Oh, here's this question. Isn't this much better?
Yeah.
Alright.
So wait, is there no AVL trees on the final?
Yeah, no AVL trees
No, everybody.
on final?
Okay.
No AVL. Yeah, what is fucking that?
That's free points, I promise you. You guys can cheat on
So let that shit ride out.
Always like. Yeah.
What does AVL mean? It's the balanced one, right?
Yeah.
So we have to balance it.
No, I only want binary.
I inserted 55, I inserted 43, I inserted 79, I inserted 35. I think I did a pretty good job so far. So after we insert 35, we're inserting 33. That's going to create an imbalance in terms of ADL. So what we need to do is we actually need to do a rotation. Because this is a left-left relationship, we're going to do a single rotation. And when we do the single rotation, 35 is going to move up, 43 is going to move down, and 33 is going to move in there. And it's after each insertion, so you imagine that the insertion is going to do the rotation for us. So what's going to look like is 35 is going to be here, 43 is going to be down here, and 33 is going to be over here. So now what we're going to do is we're going to insert 80. 80 is going to go over here. It's not going to create any balance, so we actually don't need to do any rotations. It's very trivial. So I'm sorry that I talk so fast all the time. It actually runs in my blood. I had a cousin that won a competition for like some word speaking thing, and I just thought that I was like out of the loop, and then as I got older it got worse, so I apologize. So now we're going to be inserting the element 96. 96 is going to go over here, and the thing is when 96 gets inserted, it's going to be two balanced on the side and it's a right-right. So what do we need to do to fix this? We're going to do a left rotate on what? Yeah, and that's all we need to do, right? So very easy. I mean, you guys are like, no, don't do this. This is going to be terrible. And now you're like, oh, I want this. Make up your minds. All right. Who was an easy example? Yeah, it probably was. It was. All right, so H1 is something that computes the sum of every odd integer, which is ones, hundreds, tens of hundreds. Wait, what? Tens of thousands. 10 hundreds. All right, and this is going to be tens and then thousands. So there we go, 10 hundreds. That's a good one. All right, so H2 is the sum of every even digits then. So now we need to go ahead and do mod 10 because we have only a hash size of the hash table size 10, and we're only inserting 5 values, which is okay. However, I did say we needed to do linear probing or quadratic probing. I'll probably tell you on the exam what I'm going to expect you guys to do if I do ask you this type of question. If I don't specify, I normally want you guys to do linear probing. If I say quadratic probing, it's kind of like a jerk move because I really hate quadratic probing, and you might not have enough space to do it because. So admittedly, this is a size table of 10, and I'm giving you 5 values, which means you should always be able to do quadratic probing. But quadratic probing can fail without a full array. So I don't like doing it. Anyways, let's go ahead and try this. So 561 is inserted first. So what's its H1 value? So it's going to be 5 plus 1, which is going to be 6, because it does the ones place plus the hundreds place. So it's going to be 6, then 6 mod 10 is what? 6 as well. So we need to insert it into H1 at position 6. And then we need to insert it into the second hash table as well. So it's going to go into what position?
That's going to shift over.
So what's the H2 going to return? 6, because 6 is the only even digit. And so now we move on by 10 at 6 again, and we insert it basically the same place, just in a different hash table. So now we do 2018. What's H1 in 2018? 8, because it's 0 plus 8. And then 8 mod 10 is what? So we insert here. Now we do the H2 of 2018. What's H2 of 2018? 3, because it's going to be 2 plus 1, because it's all even digits. Even is going to be this one and this one. So 1 plus 2 is 3, 3 mod 10 is 3. So now 1, 2, 3, 4, 5. What is the H1 of it? 5 plus 3 plus 1, which is going to be a total of 9. 9 mod 10 is 9. So it goes 1, 2, 3, 4, 5. And then what's the other value of it? 2 plus 4, which is 6. And now we're trying to insert it here, but we can't.
Just shift it over.
So now we linear probe.
7.
We can insert it here.
There you go.
If we wanted to access 1, 2, 3, 4, 5, how many operations would it take? 2, because, well, it depends. Like, assuming the hash function is instant, like not even like a registering, it would be, all right, we go here, we check to see it, and we see that this is not the value we want, and so then we'll go to the next spot and we'll see it. So it should take like 2 lookups to go ahead and find out where 1, 2, 3, 4, 5 is. But we'll ignore that for now. It's not like hugely important. So what about the next guy? 875. What's H1 of it? It's 13, but 13 isn't in here, so what do we do? 1 by 10, and we end up with what? So we should stick it in there. Alright, and so then what's the next one? So it's 7, so where does it end up going?
It's going to go to 8.
It goes into 8, because it has to linear probe. Alright, so now we're doing 42. Where does 42 go?
7 has to shift.
It goes, H1 is going to be what? 2. So it's going to go into that spot there, and there's nothing there, so we don't have to worry about it. 4. Easy. Now what if I ask you to code this up?
So you're putting in the mod, right?
Alright, good to hear.
Something, right?
Too bad.
And so
Good luck on the exam. Alright.
you go down, it's
How many more of these do we have?
turn.
So
So say
mother.
some of
Okay.
shift over. So we're at 1, 2, 3.
So-
It's supposed to go in 6. But since there's already
This is a fun one.
you have to go over. But say if there's
So what I want to do is I want to find out
so yeah, it's kind of shifting to that next one.
the first character or the first word that has that letter. So the thing is, Adam doesn't begin with a D, but is the first lexicographically speaking word that begins with a D. And so that's what we're going to end up using. So assuming that the trie is already constructed, how would we go about doing this?
The cursor. I know there's a
So the first thing I would do is actually the base case. So if this is, I'm going to do this recursively because honestly a lot of things when you're working with trees, it's very easy to do with recursion. So the simplest thing you can ever do base case wise when you're working with trees is do what? Check the root if it's null. So if root is equal to null, then this is not a valid string. And so what I'm going to do is, since I'm returning a char star, if in order to say that it's not a valid string, I'm going to go ahead and return null.
Oh yeah, to do with the base case.
Yeah.
And so now I'm going to know that this was a mistake. I'm not going to go ahead and do that. I'm going to do something else. Oh, it wants to do what?
No,
Well, there's more questions, you get more points. There's more like chance of you knowing something.
So, okay, this is actually something, I'm kind of jumping the gun here. I apologize a little bit. So, one thing that's a little bit of a problem, potentially, is that if, so, let's see, we might need to change the alpha value in my call is what I said here, which means that we might actually need to change this into something to say that we've already found the letter. So what I actually want to do here is not, strictly speaking, check immediately if it's null. This is a good idea, but it's going to be a wrong approach. And the reason why this is going to be wrong is because your alpha value could potentially be not a character. If I potentially found out, and this is like a really weird thing, but if for some reason when we're going through our string and we end up finding out that we can use the character, imagine we're doing Adam and we're looking for something with the letter A, then that means that I don't need to worry about finding the alpha value anymore. When I work through Adam and I get all the way down to the M, and then I realize that M has a flag set to 1, I should go ahead and say, all right, this is the letter I want to use. This is the word I want to use. And I'm going to go ahead and return that I'm going to use this guy. But the thing is, if I'm still passing an A, I might be like, oh, M unfortunately doesn't have the letter A in it, and because of that, we can't really do anything with this. Let's just move on from here. So what we actually want to do is we want to check to see if not only if the root is null, but also if our alpha value is still a valid character. So what I ended up doing is I kind of like did something sketchy, where I was like, this is a valid character, you know, it's in the range of A to Z. if we're still looking for the value. And then otherwise what we'd end up doing is I would set it equal to a null terminator. And if it was ever a null terminator, then that means that I've already used my letter inside my try, and I don't need to worry about using it again. So I also additionally checked in this state here that alpha is not equal to the null terminator.
Okay.
If the root is equal to the null and alpha is the null terminator, this is another base case.
No, it's two base cases.
I need to create some string that we're basically going to be using for the rest of the eternity or whatever. So assuming that we have strings at h, we can go ahead and do some stuff, but we don't really need to use that right now. Instead, since we're at the null, we can just basically pass in an empty string. So to return an empty string, what we do is we just go ahead and we create string char star ret is equal to char star callic. We'll do one size of char. And then what I do is I say ret of 0 is equal to the null terminator character to say that we're passing back an empty string. So then what I do is I do a for loop for all of my children at this node. And I'm going to go ahead and look to see if I can build up a string. And since I want to do this lexicographically first, what I'm going to do is I'm going to loop through the first child, which is child 0, and I'm going to go to Z. Because if I can ever construct a word with a smaller letter first, then I'm going to return that over returning anything else. So we're going to do the smallest letter first. I think I drew 2 backslashes instead of 2 forward slashes. Yep. All right. All right. So what we're going to do is I'm going to have like some int I up here so that way I can go ahead and use it because I don't like doing my declaration inside my loops. For I equals 0, I is less than 26, I plus plus. And so now what we do with this is we try finding a string. So we do char star ret is equal to find first string when letter. And now we're going to pass in something different. So if we're now reading this root node, what we want to do is we don't want to go from the root node anymore. We want to go from this child that we're using. So we're going to go ahead and say root children bracket I. And now what we need to do is we need to use this alpha. But the thing is, if we are using the correct value, we don't actually want to use this alpha. We want to use the empty character instead. We want to use the null terminator. So what I'm going to do is I'm going to go ahead and say if alpha plus A is equal to, biscuits, and then do I plus A.
Yeah.
Well, there's an easy way to fix this. Subtraction sign. If alpha minus A is equal to our I, then that means that we're using the character we want to be in our string. And so if we're using the character we want to be in our string, I just realized, yeah, there was that other, I'll get to that. I'll do that. Don't worry about it now. Worry about it in the future. All right, so if alpha minus A is equal to I, what we want to do is I'm going to use the ternary operator here. I'm going to go ahead and say we don't need to use this value anymore, so we're going to go ahead and use the null terminator instead. And then if we're not able to say that these values are equal, we're just going to use whatever our previous value was. If our previous value was a null terminator, this is never going to be equal, and so we're always going to be using a null terminator. And if this value is ever not part of the null terminator, then we're going to be using whatever the not null terminator was. So this is going to be okay. Then what I need to do is I need to check to see if this value is null. So if ret is not equal to null, not equal to null, then that means that what we ended up doing was we found a solution. So what we want to do is we want to do something else. And then down here, we're going to go ahead, this is outside the for loop, we're going to go ahead and return null here. Because the idea is, this is actually a backtracking solution a little bit. What we're doing is we're trying to use the letter. If we can, we do it. If we can't do it, we go ahead and return null, like, hey, we can't possibly solve this. But backtracking, I guess, would have a valid function. And we don't really have a valid function other than the root check, but we'll ignore that for now. So if the ret is not equal to null, then that means we found a solution and we need to return it. But the issue is this ret is going to be one character too small. And the reason why is because it found basically the substring minus this one character we're using. So what we need to do is very unfortunate. We need to actually resize ret. We need to go ahead and move its data back one, and we need to insert the new character at the beginning of it, which is really nasty sounding. And it's not terrible. So we need to make a char star new ret, and this is going to be equal to callic. And you would want to do a cast here, but for the sake of time and a few things, I'm not going to do it. We're going to do str lang ret plus 1, actually plus 2, because we need the null terminator as well. And then this is going to be size of char. And then what we do is we copy in the ret, but we don't want to copy in ret first. We want to make sure that new ret is equal to this one character. So what we do is we say new ret 0 is equal to I plus A. And then we say new ret 1 is equal to the null terminator character. And then the last thing we need to do is we need to fill in new ret with all the old stuff. So we say str cat new ret comma ret. And then we need to return new ret. That is a fun program. All right, and that's the end of that parentheses for that guy over there. And then this one is the end of that parentheses over there, which is weird. So the last thing I just realized that I forgot to do is here, I think someone even said this earlier, and I'm sorry for disregarding it. We also need to check to see if the flag is equal to 1. If the flag is equal to 1, that means this is also a valid string, because it could be a shorter string that's in our substring. So we need to check to see if the root is equal to null. Oh, it's not there. Where is it? Yeah, no, it is there. Oops. If the root is equal to null, or alpha is equal to the empty string, and flag is equal to 1. And the reason why we need to do this check in there, that's terrible looking. But the reason why we need to do the check there is because we need to make sure that if this is a valid string, we're using it instead of continuing on. Anyways, so the last question is very easy. I'm going to go ahead and breeze through it, and then I'm going to work on exam 2 stuff, even though I'm a little over time, I apologize. So the get function will return a value unless the value doesn't exist, it'll return null. The void is always a void function, so it doesn't return anything. So we just do them in this order. So this is going to be null because there's nothing in there. Then we put in u with 5, put in me with 3. We get me is the value of 3. We put in them with a value of 4. We get me is still 3. We get them, which is going to be 4. We get u, which is going to be 5. I didn't, oops, my gosh, what did I do? This is supposed to be 3, 4, and then 5. I'm like not lining up. And then we put in us, that's not going to return anything. These are all void. If you want to write void, you can. Because it returns technically nothing. But this is all that you end up needing to do for this problem. Pretty simple. Let's see. So I wanted to do one of them that was on the first exam. I think someone said that they wanted me to do this problem. Is this the one you wanted? Is it this one? No? I can do a different one then.
I think that was it. Yeah, that was it.
That was it?
That was the one I liked.
This is the second exam. So I'm just going to go ahead and really quickly do this problem. So I know that some people weren't here when I did this solution the first time. So what you want to do in order to find out what the tree that would have this valid thing is, you notice that's a binary search tree. This element must always be the root because that's how a post-order traversal works. So 10 must be the root. And then if 10 is the root, you know where every other element needs to go, either on the left or on the right side. So where does all the other elements go? They all go on the left. So all these other elements need to go on the left-hand side. And so in order for them to go on the left-hand side, what we need to do is we need to figure out the new tree that's going to be on the left-hand side with these elements. Now it turns out that this is just going to be a valid pre-order traversal, or sorry, post-order traversal on whatever this side is. And so the last element of that needs to be the root of this subtree. And so the last element is going to be 5, so this 5 is going to be the root of this subtree here. And so now you know where all the elements need to go, either on the left or on the right side. So what elements are going to go on the left side? So these are going to go on the left side. What elements are going to go on the right side? Alright, and so now we need to construct trees recursively doing this process. So the root of this tree here is going to be whatever the last element of the subtree of this sequence was. So the last element is the 6. So 6 is going to be the root. And then what we need to do is we need to figure out where all the elements are going. So where do all these elements go? They're all going to go on this side, right? Because they're all larger. So the largest element is going to be 8. 8 is going to be the root of the tree. And then 9 needs to go on one side, and 7 needs to go on the other side. And it's very easy to do them. That's going to be the tree so far. And now we need to work on the other side because we kind of neglected it. So what's going to be the top element of this subtree? So then where are the elements going to go? And then 3, 4 are going to go on this side somewhere, right? What's going to be the top element? And then this one has to be over here. And now if we want to do, we can very quickly do a post-order traversal. So the post-order traversal will go down here. It'll print out 1. Then it'll go up, go down, we'll print out 3. We'll go up to 4, print it out. Go to 2, we're now weaving 2, so we'll print it out. Go down, we go up to 5, we're not weaving it, so we don't print it out. We're not weaving 6 yet, not weaving 8 yet. We print out 7. We print out 9. We're leaving 8, we print it out. We're leaving 6, we print it out. We're leaving 5, sorry. We're leaving 5, so we print it out. And then we're leaving 10, so we print it out. And so this ends up being the order. And so if you notice, it is the same. I hope it is anyways. Alright, cool. So this is how you can go ahead and construct a VST from a post order, as long as it's a search tree. If it's not a search tree, there's multiple ways of doing it, and that becomes a nightmare. If I give you a pre-order and a post order, do you think it's possible to construct a tree even if it's not a search tree?
Maybe.
If we believe.
I couldn't give you the tree. What's the pre-order of this one? Okay, that's cool. Maybe, we'll see. That might make its way to the exam. All right, is there any other questions you guys have on the second exam? I can do any problem right now. I don't really like posting the answers for exams. I don't mind going over them. It's a little weird. Maybe I'll end up doing it. Then we'll have to withdraw deadline. Just don't post it on any weird website, okay?
Okay. Promise.
These answers here? Yeah, I'll post those. I don't mind posting those. The tests are not stapled. So the answer to that is no, not really. I can try to have them by next week, but I don't know if that's going to be a possibility. I can go ahead and go over the solutions with you if you guys want, but I think that I don't mind doing the answers for this one because I don't have the guys stapled and handed back to you. So I'll do that. I'll post the solutions, I guess, and the test too, and I'll get around to doing this other one. Is there any questions you guys have for me? You can come up, talk to me, raise your hand, jump around.
I still have something that isn't.
I gotta go talk to you.
Let me know what he says if you're gonna ask him to pass it.
Alright.
I'm gonna go get food and then text me what room you end up at.
Alright.
The human interaction was what? That class was super easy.
It is. She just like, whatever, if it changes your grade, I'll like, if it changes your grade, I'll do a grade update, but, the TAs fell behind, like, we never got anything.